So we are now going to continue with the linear data structures. Particularly, we are going to talk about a queue. So now queue, just now when we talk about stack, stack is last in, first out. Queue is first in, first out. So Singapore, we are a queuing nation, right? So we kind of understand what a queue is, and we expect everybody to follow the rules, right? So these are just some famous examples of queues when they were selling Hello Kitties and McDonald's. There were long queues. But the idea is that the first person that enters the queue should also be the first person who leaves the queue. So between two elements, the one that goes in earlier that should also be the one that leaves earlier. So the same way when there is a new iPhone coming out, there is always a queue. Now, of course, in terms of computing, we use queue for different purposes. But for example, you might use it to control access to resources. So it could be that you have a common printer that everybody prints through. Then in that case, you want to create a system where if you send the queue job first, then the printer is going to deal with your queue first. Okay, queue is basically quite straightforward. Now the basic operations, some of them are the standard ones, like you basically want to know what is the size, whether or not it's empty, right? Now, but the most important thing here is to imagine that in the queue system, right? So you have what we call the first element. Now, so we don't call it top anymore. Top is for stack, so we call it first. First means that then there is there are the ones that actually follow. So when you queue something, when you join the queue, you call it enqueue. So then that happens that it's gonna go to the end of the queue. When you are leaving the queue, you call it dequeue. In that case, you are leaving from the front of the queue. Now, we can consider different ways to implement this, and following the discussions on the stack, you can kind of get a sense of the different ways in which we can do this, right? Okay, but first maybe let's take a look at just a simple example. We basically do the same operations as we did for stack, but now instead of push and pop, we have enqueue and dequeue, and it's going to create pretty much a different kind of behavior. Now, the first element here is basically the first element or the head of the queue. What follows is basically behind, right? So when you enqueue 5, then 5 joins at the front. So this is the first, right? And then 3 joins behind 5. And in that case, when you dequeue, 5 is the one that leaves. And when you dequeue again, then 3 leaves. When you try to dequeue again, well, there is nothing, right? So there is nothing to return. But you enqueue 7, 7 becomes the first, 9 follows, followed by 4. So when you dequeue, then you're going to remove 7, because 7 is currently the first one. Enqueue 6 and 8, so you have 6 and 8. And when you dequeue again, you're going to remove 9, right? So then the remainder is going to be 4, 6, and 8. Okay, alright. Now, how do we implement a queue? So we're going to discuss again two different implementations. One is using an array, and the other one is using a linked list. Okay, so let's take a look at the array first. Now, this is the implementation for a queue. So again, we have the capacity, and we have the data array that basically contains this, right? And we have the following parameters that tells us what is currently the first or the front of the queue, and what is the size of the queue, right? Now, size here means the number of data elements that we currently have. Alright, these are the constructors that is going to create an array of either the default capacity or some capacity that is given in the argument. And if you want the size, then you just return the size. Okay, so if it is empty, then we will take a look whether or not the size is 0. Otherwise, if it is a first, then you just return it. Now here, we want to implement a queue, right, using an array. Now, if this is the data array, right, so where should we put the first or the head of the queue? Now, because we call it first, a natural way to do that is put it in the beginning, right? And if you put it in the beginning, then what happens here is that I'm going to go all the way to n minus 1 now. So when I have an nq, then a new element is going to join in, let's say A. Then the next one, B would join, later, right? But in that case, I just need to put in into the end of the thing. I don't have any shifting to do. Now, but if I were to DQ means I'm going to get something out. Now, which means I'm going to take A out and I'm going to move B into it. So which means that I will need some form of shifting all around. And that is kind of what is being described by the following implementation. We're going to start from the first element at 0, right? So this is the first. And as the new elements join in, they're going to join in at the end of the queue. So every time we enqueue, basically we just need to put it to where the size currently is, because the size basically is going to tell us the next position that is empty. And of course, after every insertion, then we have to increment the size variable. Now to DQ, this is where the shifting is happening, right? Because the element that is currently at the first, we want it to leave the queue. And if we want it to leave the queue, it means that everything else has to shift to the left, right? So that means that if we were to DQ A, then B has to go to where A is, C is going to go to where B is, and D and so on, right? So now this is expensive because every time we do this, we have to do so many operations. So what can we do? What can we do, right? Well, just now when we talk about stack, we had a lock by putting the top of the stack at the end of the array. So what if we consider that? So what if we want to have a system where the head of the queue is always going to be the last element that is not empty? So in that case, for me to DQ, then I just need to remove that, right? And then my head would then be in the previous position. Well, technically yes, but now I'm basically just shifting the operations to the NQ. Because now when there is a new element that joins this, because I want my head to be, my first element to be at the end, so the new element that joins in has then to push everybody forward to make room, because they're going to join at the end, right? So now we are not really gaining anything by putting the first element at the end of the list. But luckily, there is yet another way, right? So the question is that, can we avoid the shifts? Well, there is actually a clever way to do this. You can kind of maybe even pause the video for a while and just think through what you could do to make sure that you don't need to do any kind of shifting. Now, the basic idea of being able to avoid the shift is based on the concept that you're going to be moving the pointers instead of be moving the elements, right? So that is what we will try to do, and in this case we call it a circular implementation of a queue. Okay, so the keyword here is circular. Now let me first try to describe the idea first, right? So let's say you are given an array, and in this case you have what you call like the first element, right? And then you are putting in a lot of different things here, right? And let's say at this point of time, this is basically the last element, right? Okay, so you have the first and you have the last element. Now, if you want to enqueue something, then it's just going to join at the last one, right? If you want to dequeue something, then it's going to leave the first. Now, previously what we're going to do is that we're going to shift everything down. But let's say instead of doing that, we're just going to say, okay, my first is not going to be here anymore. I'm just going to turn it into a null value. I'm going to point to this one now. So in that case, I don't need to be shifting anything. Now, if I were to dequeue one more time, then I'm going to turn this off. Alright, just set it to null, and then I'm going to repoint my first to this one. Then in that case, I'm just going to point my thing to this one, right? Now, so in that case, basically the first is going to move forward, and so is the last. So that means it's always going to be moving forward as well. Now, the issue with this implementation is that at some point, we are all going to be right at the end of the queue, right? And at that point of time, you keep adding. So let's say now, at some point, the last element is actually really at the last one. Okay, so let's say it's really at the last element, right? Now, and then I want to enqueue one more time. Well, there is nothing here, right? This is outside of the array. But there are all these empty spaces that have been vacated every time I dequeued something. So in that case, a reasonable way of doing this is that now I can insert the next element actually circularly by going to the beginning again. So which means that now I'm going to have a particular situation where I can have my first to actually be behind my last. That's kind of counterintuitive, but it doesn't quite matter because now we have a circular implementation of this, and in this circular implementation, basically we have the first and the last. They keep going around in a circles, and the way we can achieve that is through the mod operation. So in this case, we know what is the current size of the queue in terms of the number of elements. So which means that if the current size, let's say, is 10, right? Okay, let's say you have an initial array, right, of, let's say, size, okay, let's make it simple. Let's say size 10, right? And currently, your first element, okay, is currently at size, okay, F, right? And your array size is currently 4, queue size, right? So which means in this particular case, the ones that are being filled in is position 5, position 6, position 7, position 8, right? Now 5, 6, 7, 8, this is where your queue is. Now when you are going to enqueue one more time, then you're going to turn 4 into 5 now, and you're going to also continue and occupy the position 9, right? Let's say you want to enqueue one more time, and in that case, your current size now is already, well, 5 and 5, right? So where's going to be the new position? Well, in this case, you know the next position should be 0, because there is nothing else after index 9 if your array size is 10. So then, based on the following function, so what you're going to do is that you're going to take the f, and you're going to take the size of the queue, and just sum them up. Now, this may actually be exceeding your current size. So in order to know where in the cycle you are, then just take the mod of the whole length of the array. So in this case, 5 plus 5, 10, 10 mod 10 is 0. So which means that the next item you're going to put in is going to be 0. So this is the first, and this is now the last, right? So now we have a queue size of 6. Alright, so then if you increment one more time, then in that case 6, okay, 5 plus 6, 11 now. 11 mod 10 is going to be 1. So then it's going to be basically be cycling forward. Now in the same way, when you dequeue, we are going to just need to take something from the first element, and then we are going to set it to null. Then we just need to increment the f by 1. So for example, if you are going to dequeue the position at 5, then you're going to replace it with 6, right? Now we just have to be careful that at some point you're going to jump over the cliff, right? So which means that you're currently at position 9, and then if you're to increment it by 1, you'll be at position 10, which is an empty space. So in that case, you're going to cycle forward to the beginning. So that's why you need to make sure that you get to this mod as well. All right. Now with this kind of cycle operations, to enter it is one, to exit it is also just one operations, right? In the sense that there is no shifting involved. All right. So the next thing is that, of course, you know, other than having to deal with all these arrays, you can just use a linked list. And if you use a linked list, then you can keep track of what is the head and the tail of the list. So for example, if you're going to enqueue, you join it at the tail. So add something at the last element. And if you're going to dequeue something, right, then you're going to remove it from the first element. So in that case, basically your first, okay, then it's gonna point to the next one, right? And then finally you're gonna get to the end, right? This is the end of the queue. So for you to dequeue something, you just have to remove this and redesignate the first to be the next one, and the first is going to be removed, and this is going to be the new first, and then you have the end part here, right? Okay. All right. So now for this is regular queue. Now we can talk about a double-ended queue, and okay, so here we call it deck. Okay, this is not dequeue. So dequeue will have another UE behind it, right? So this is a deck. Deck is a double-ended queue. Now a double-ended queue, it means that you can actually choose whether you want to enqueue and dequeue from the beginning or from the end, right? So in that case, this is the abstract data type of deck. So here you have the first, you have the last, and you can either join the queue from the first or from the last, and in that case we can also remove it from the first or from the last. Okay, how would you implement a deck? Well, there are some very natural ways of doing this. So in that case, I'm just going to leave it to you as an exercise. All right.